Welcome to my projectbazaar.com. Let's discuss about the product. Our product is increase in read noise margin of single bit line SRAM using adiabatic change of word line voltage. A single bit line static RAM, that is SRAM circuit, that employs adiabatic charging of a word line during a read operation was found to provide a large dynamic noise margin for reading. Single bit line reading is achieved by using a left access transistor and a shared reading port. The shared reading port greatly reduces the bit line capacitance, enabling the voltage of the bit line connected to the low voltage node of the flip-flop to change from the precharge voltage to ground. An analysis of the two-wise change in DNM revealed that the read noise margin of this circuit was 1.9 times larger than that of a conventional 2-bit line circuit. This circuit enables the design of an SRAM that is smaller than a conventional one, resulting in lower energy consumption. Wireless sensor network technologies are attracting attention in emerging applications such as industrial monitoring and security surveillance. The paper proposed is the power available to a wireless sensor network is limited because it comes from a battery or supercapacitor. Thus, network nodes must have the capabilities of low power sensing, processing, and communication. Since a static RAM is a key circuit in a sensor node, it is important to reduce its power consumption. A graph of power consumption versus frequency reveals two frequency regions. From 300 MHz to 1 GHz is the high-speed range used for communication in high-speed routers, and 8 MHz and below it is used for low-speed range and for home industrial appliances, wireless sensor networks and other low applications. Our target is even smaller power consumption. One way to reduce the power of an SRAM is to reduce the supply voltage. The way investigated in this brief is to reduce the device size to the nanometer region. Reducing the device size by 1/2 cuts the gate capacitance by 1/4, which should result in a large reduction in power consumption. However, if we try to use a nanoscale SRAM in a system, we find that the static noise margin is too small due to the large variation in threshold voltage. So we have to develop a new SRAM circuit. Our previous study of SNM showed that the SRAM with a single bit line had a larger SNM than one with 2 bit lines, and that the bit line precharge voltage should be lower than the VDD. In this paper, we attempt to adiabatically charge a word line in a single bit line SRAM to stabilize the flip-flop. Adiabatic charging has been widely investigated and it is already being used to charge the cells of plasma display panels. We found that it significantly increases the dynamic noise margin for real operations. This flow diagram states about our system flow which we used for this development. So initial black which is states as a CMOS design, that states about our design methodology, because our design methodology is based on CMOS transistor based designs. For this CMOS based transistor designs we are using Tanner EDA tool. So, and as we already discussed, our main focus is based on bit lines, whether it is single bit line or 2 bit lines. Hence, we have denoted the bit line importance there, and the main black is noted here as heterogeneous CMOS, because the heterogeneous CMOS is our enhanced method. That means Here we have noted heteroCMOS. HeteroCMOS represents heterogeneous methodology. Heterogeneous methodology is a technique which we are implemented in this paper as an enhancement. So finally, our overall design provides the SRAM cell. As usual, we are providing a conventional operation like write and read. During the read operation, we are performing the parameter measurements. Due to the parameter measurements, we can identify the possible parameters such as accuracy, complexity and noise margin. So as our goal to reduce the noise margin, we can measure the noise margin with our proposed design and we can compare with the previous methodologies. It will give better performance results than the previous designs. Let's discuss something about the tool. For this CMOS design based methodologies, we have to use CMOS design tool that is called Tanner EDA tools. Commonly, Tanner EDA tools having lot of subdivisions that is called SEdit, LEdit, WEdit and such more. There are lot of under devices. So in this we are using SEdit for circuit designing. So and then after we design that SEdit, while simulating the circuit's design will pass through the T-Spice that we can understand through the checklist generated through the SPICE code. And finally, while we are simulating, the timing diagrams will appear in WEdit. Hence, commonly for our CMOS based designs, we will use mostly these three edit things. That is, again I will say as SEdit, LEdit, WEdit and T-Spice. So we can design the circuit based CMOS transistors by using SEdit. Here, before we starting the simulation, we have to select a new cell. Here is a cell menu. Here we have to select the cell menu and we have to select new cell. So there you can select number of cells like cell 0, cell 1 up to cell n you can select. So each cell should contain different CMOS design. And next process is to set up simulation. Here this icon, while you are pressing that will leads you to set up simulation. In the setup simulation, you have to set up maximum time duration for the design and nanoseconds based setup methodologies. After designing setup designs, we have to load the library files. So initially for the design of CMOS designs, we need some CMOS components. Those CMOS components will occupy in CMOS libraries. That means CMOS libraries contains components of which required for CMOS design. So here you can see what are the components listed in CMOS library. While you are pressing add, it will leads you a window menu. There you can locate the library file where you have stored. So from the location where you have stored, you can select all components which you can need for your CMOS design. So after design of this cell, you can save the design, and while you are pressing run, it will leads to T-Spice. So through T-Spice, you can see what are the checklists available in T-Spice. In T-Spice, usually the components which you have used are listed in as a component code. That means you can see that as a program wise. That's why that T-Spice codes are called netlist. You can run either from SEdit or from T-Edit. From wherever you are running, the output timing diagrams will show in WEdit. In WEdit, you can see the waveforms which we have obtained for corresponding CMOS design. And also you can clarify what are the result parameters, and you can measure all the parameters which you need for the design from the WEdit. Thank you.